Hello, everybody. Thank you for joining this IMechE lecture. We are recording this session right now, so please be aware of that. This webinar is being recorded and it will be made available later through the IMechE YouTube channel. You will be sort of provided with the slides later on, PDF slides. I am Murat Islam, a member of the IMechE Power Division and Greater Manchester area. I'll be sort of managing this event, hosting it, and I will also direct your questions at the end to our speaker. We will sort of allow 10 to 15 minutes for the Q&A. So please use the chat function to submit your questions. So with that, I will introduce our speaker, Mr. Daniel Wells. He is the National Consultant Specialist for Spirax Sarco, providing educational, technical, and commercial support for consultant design engineers, engineering, procurement, construction, and contractors all across the UK and the Republic of Ireland. Working closely with the Spirax Sarco's area engineering project teams, Dan has many years of experience with broad range of industrial applications, working across many engineering disciplines. Thank you very much, Daniel. You can start your presentation.
Great. Thank you very much for that introduction, Murat. Much appreciated. And thanks also to your colleagues at the IMechE for making tonight's event possible. It's much appreciated. I'd also like to take a quick moment just to show the respects on behalf of IMechE and Spirax Sarco in the event of the passing of the Queen last week. So our joint respects go out to Her Majesty and the royal family. Moving forwards, as Murat said, with light of tonight's presentation, it is being recorded and it will be uploaded to YouTube on the IMechE channel in due course. But please do take advantage of the chat function that we have on tonight's Microsoft Teams channel. So any questions or comments that may arise, then please do drop them into the chat function. And when we get to the end of tonight's presentation, Murat will open up the microphones and we'll be able to address anything that may warrant further attention. I believe Murat will also be sending out a feedback form once the presentation's finished. So if you could take a moment to add your feedback, it would be much appreciated. We'll also have a PDF of the slide pack that's made available should that be of interest. So my name's Dan Wells. I'm the National Consultant Specialist for Spirax Sarco, UK and Ireland. And for those of you who may not be aware of Spirax Sarco, I'd just like to take a moment to introduce our group of companies. Well, Spirax Sarco is a global entity. We operate across a number of different countries and our headquarters are down in Cheltenham in the UK. We're also a FTSE 100 listed organisation, but we operate across three different distinct divisions. We've got our Steam Specialties division, who I work for, and we've also got our Electric Thermal Solutions division. And the reason that's of particular interest is the group of companies that fall under that division: Chromalox, Thermocoax, and most recently Cotopaxi, that's based up in the northwest, and also a company called Volcanic, all form part of the Thermal Solutions division. And collectively, they've got a significant amount of interest in enabling us to generate steam sustainably from alternative sources such as electricity. And that's going to become more relevant as we go through today's presentation. So as far as Spirax Sarco in the UK and Ireland's concerned, we're a team that's approximately 200 strong. About 50% of us work from home. And that comprises not just specialists such as myself, but sales engineers, project engineers, commissioning engineers, and product specialists. And we work remotely, so we're never too far away from any of our clients' sites or indeed their offices to offer any support that may be required. But one thing that we do have at Spirax Sarco is we've got a very, very powerful suite of calculators, configurators, and tutorials that are accessible via our website. And you can actually take that one stage further. We've got a suite of very, very useful calculators and configurators that can be downloaded in the form of an app and used either on your Android phone or your iPhone. So you can take that information away to site with you. Very, very powerful information to help us understand not just some of the design considerations that we have with the Steam system, but to also help us to accurately calculate the cost of Steam. So if we're able to engineer a solution that reduces the amount of steam that's being used, or we can reduce any unnecessary heat losses, or maximize the amount of condensate we can return back to the boiler house, then of course we can demonstrate a payback. And as we all know, any project that can identify a payback is more likely to reach the top of the pile. But it's not just payback in financial terms. We also know that if we're using less steam at the process, we're burning less fuel. And if we burn less fuel, the carbon emissions are going to be fewer. So one thing that we're all aware of is that it takes a considerable amount of energy to produce steam. In years gone by, that's been coal, more recently oil, and at the moment we use a considerable amount of gas to raise steam. So quite often energy managers, sustainability engineers, they've quite rightly identified the amount of energy that is consumed to raise steam. So today's presentation is really going to look at the future of steam, where we're heading. We've all got very, very lofty sustainability challenges and sustainability targets. So it's easy to paint a bullseye, to paint a target onto the head of steam and identify steam as being a dirty, dangerous, or difficult source of energy to control. And that's simply not the case. So as we go through today's presentation, we're going to discuss why steam is and will continue to be relevant for the vast majority of manufacturing processes. We're going to look at the fundamentals of steam, and then we're going to look at the different solutions that are coming up in the elevator that are at a very, very advanced stage of commercialization that will help us to move towards, if not totally achieve, net zero with our steam systems in the very near future. So just to remind ourselves, steam is actually used in a very, very wide and diverse range of industrial applications. In fact, it's true to say that steam is used in some form wherever a product is being manufactured or processed. And there's a number of reasons why that may be. And we'll go through that in due course to identify the physical properties that steam has and to explain why it continues to be such a valuable and useful source of energy. So just to remind ourselves on the challenges, and I believe we're all very, very well aware of what the challenges are. Well, we appreciate that we've got a very, very ambitious target to hit. And originally, that target was to see a 90% reduction of the year 1990s carbon emissions realised by the year 2050. And of course, over very recent years, that's been revised considerably for an even more challenging and an even more ambitious target to achieve net zero by the year 2050. Now, we remind ourselves that that's just 28 years away. And that's going to be a target that's very, very difficult to achieve unless there's a significant and fundamental shift in the way that we're generating and utilizing energy at the process. But as far as the sectors that we operate in are concerned, the industrial and the manufacturing sectors, we appreciate that thermal energy is by far and away the largest cause of a draw of energy or carbon emissions, by far and away. So we know that there's been some considerable steps that have been taken by the government over recent years to drive down carbon emissions in certain sectors. For example, road vehicles, the shift towards an improvement in the number of electrically operated vehicles that there are out on the roads. There's been a significant shift there. But unfortunately, that's a drop in the ocean when you compare that to the carbon emissions that arise as a result of the industrial and manufacturing sector. And we know that steam is by far and away one of the biggest and most important sources of thermal energy. And therefore, it means that in the very, very near future, that target that's painted on the head of steam is going to become more and more prominent. Now, Spirax Sarco, as a FTSE 100 organization, we're a member of what's called the FTSE for Good Index. And it really emphasizes the fact that we recognize we need to lead by example. So, as far as our own energy consumption is concerned, we've given ourselves even more aggressive targets to hit. So, we're wanting to move towards a complete shift away from fossil fuels by the year 2040. But we've also identified that we want to see a significant reduction in other sources of energy by the year 2030. And the reason that's relevant is because if we've got these targets, if we're imposing these targets on ourselves, then we recognize that so many of our clients, especially in the blue chip or multinational corporation sector, they're going to be looking to do likewise. They're looking to act today. So the presentation is really going to focus on two things. First of all, why steam will continue to be relevant tomorrow, but also how we can help our clients continue with their process and retain their existing infrastructure simply by generating steam from an alternative source. So moving forwards, let's look at why steam is so very, very well received in so many industrial manufacturing sectors. Simply put, it's because steam is so densely packed with energy. Up in the top left-hand side of the screen, the little table, it really reminds us that the only way that water can give up its heat energy is by cooling down. So if we've got a kilogram of water that cools down 11 degrees in order to give up its energy to a process, well, if we compare that kilogram of water to a kilogram of steam, there's far, far more energy contained within the steam than there is the water. In fact, it's true to say that there's 50 times more energy in a kilogram of steam than there is in a kilogram of water. So if we look at the image up towards the top right hand side of the screen, that really reminds us that we can get far, far more energy down a steam pipe than we can down an electrical cable as an alternative. Down in the bottom left hand side, sorry, the bottom right hand side of the screen, you can see that that therefore means that because there's so much energy contained within a mass of steam, and because steam is after all a compressible gas, it means we can distribute that steam, we can move that energy hundreds, thousands of meters around site in a very, very small and cost effective infrastructure. Something that we can't do with water because it's not a compressible fluid, because there's far, far less energy contained within it. But furthermore, we don't pump steam. Steam's a gas and it moves in accordance with the pressure drop around the site. So if we're generating steam at a very high pressure and using it at a much lower pressure around the network, that steam will move from the higher pressure to the lower pressure without the need for any circulating pumps. If we compare that to low temperature hot water as an alternative, yes, we've got less energy in the water. Yes, we need a bigger infrastructure. We're also going to need to provide a circulating pump in order to move the energy from the point of generation to the point of use. So we're going to be drawing more energy, more electricity in order to move that heat. Now, quite often when we're talking to the industrial, the manufacturing sector, from time to time, an energy manager or a sustainability manager may mention to us the viability of a heat pump as an alternative. Now, just to make things clear, there's absolutely nothing wrong with a heat pump. We've got absolutely no argument with a heat pump, and heat pumps very much have the place in certain processes. But for processes that require a significant temperature or a significant heat content in the primary media, heat pumps are likely to be completely unable to achieve that pressure temperature relationship that steam can. Furthermore, we're going to have to circulate a significantly greater mass of water away from the heat pump, meaning that that infrastructure downstream of the heat pump is going to be far, far larger. If we're looking to replace steam with hot water that's generated from a heat pump, we've got to rip out the infrastructure, replace it with a much larger infrastructure. And then we've got a much greater draw of electrical energy from the grid in order to generate that high temperature and then distribute it to the point of use. So if we can find some alternative way to generate steam without a reliance on fossil fuels, then we will have addressed a significant number of challenges that our clients have and help them to retain their existing infrastructure. Now, just to remind ourselves what some of those high temperature, high pressure processes are, they can range from the food, beverage, pharmaceutical, chemical, pulp and paper sectors. That's by no means a limited list, but any manufacturing processes that needs a high pressure and high temperature, it's highly likely to have a requirement for steam moving forwards. Now, before we look at some of the solutions that can help us to generate steam from alternative sources of energy that don't have a reliance on fossil fuels, I just want us to go very, very quickly back to the basics, back to first principles to remind ourselves of the fundamentals of steam. Well, down in the bottom left-hand side of the screen, we've got the steam tables. There's a lot of very, very powerful information shown here on the steam tables. If we're moving away from the left-hand side of the screen, the first two columns, that demonstrates the pressure temperature relationship that steam has that other sources of energy, such as low temperature hot water, simply don't have. In other words, if we know the pressure that the steam exists at, we know its temperature. If we want to hold the steam at a certain temperature, we can achieve that by manipulating the pressure. So we also know that water, that's the raw ingredient of a steam system, water's got a specific heat capacity of 4.19. So the column that's highlighted in orange, that tells us the energy that needs to exist in the water before it will hit boiling point. And that's going to vary in accordance with the pressure that we're generating the steam at. So if we're just generating steam in a kettle in our kitchen at home at 0 bar gauge, that water needs to contain 419 kilojoules before it is boiling point, because after all, water boils at 100 degrees. So the maths is simple. 4.19 multiplied by 100. Now that's how much energy the water needs to contain before it boils. If we're putting water that is already at a significant temperature with a significant energy content into that kettle before it hits boiling point, then of course we need to top it up with far less energy in order to achieve that. And the next column, highlighted in blue, that really emphasizes the energy that we then need to add to that boiling water to make it fully evaporate, boil off, change state from a liquid to a gas. We call that the enthalpy of evaporation. And you can see there's a significant amount of energy we need to add to that already boiling water in order for it to do that. But the thing here is that energy isn't lost. The steam carries that energy and it gives up the energy at the process, at the heat exchanger. And it's the same energy that we add to the boiling water to make it change state. It's that same energy that passes across the thermal barrier into the process. So think of that as the useful heat energy. So the column that's next to the box in blue that's marked steam, that's the combination of the two previous columns, if you like. We call that the total heat. But of the total heat, the box in blue is the useful heat. And then after the steam's given up its useful heat energy to the process, to the heat exchanger, the energy that is left behind in that condensate, well, it's exactly the same as the energy that we added to the water to bring it up to boiling point. Now, in reality, our client is going to be generating steam at higher pressures. We'll use the example of 10 bar gauge. At 10 bar gauge, the benefits are, well, the steam's going to have a higher temperature. Because of the pressure, it's going to have a smaller volume, and therefore we can distribute it in a smaller, cost-effective infrastructure. And it also means we've got some good motive energy in the steam as well. We're likely to be able to distribute it hundreds or even thousands of meters to the point of use. But what you'll remember is it's the box that's highlighted in blue. That demonstrates the useful energy content of the steam. So that's the information we use to size the heat exchanger or size the requirement of the process. And you'll notice there's more useful heat energy in steam at a lower pressure than there is at a higher pressure. So that's another reason why we want to reduce the pressure of the steam as low as we possibly can at the point of use to ensure it's operating with maximum efficiency. Now, if we quickly move across to the opposite side of the screen, that's what shows the temperature enthalpy curve. In other words, it plots the journey that water takes as it changes state from a liquid in the boiler to produce steam as a gas. So the orange line, that demonstrates the energy that we need to add, in the case of 0 bar gauge, 100 degrees, for the water to hit boiling point. And anything more than that is going to result in the water starting to evaporate to produce steam. But it's only when we've added all of the energy that's identified in the blue box that we're going to get 100% dry saturated steam. And from an energy efficiency perspective, that's critically important. Simply put, if we don't have dry saturated steam, the steam could exist in the wet steam zone. And the problem that's going to result in from an energy efficiency perspective is we're going to get more heat loss in the infrastructure. We could be generating 10,000 kilograms of steam per hour in the boiler, but we could fail to get anywhere near that at the heat exchanger. So, of course, the boiler's got to work harder to overcome that inefficiency. And the harder the boiler has to work, the more fuel it has to burn, the greater the inefficiency and the more the carbon emissions. So we want to generate steam as dry as we possibly can in order to emphasize that efficiency. The other reason is if we've got any heat loss in the infrastructure, as the steam travels hundreds, maybe even thousands of meters around the infrastructure, as it passes across those condensate losses, the steam's going to degrade. So it's going to move further away from the dry saturated steam zone. And if you look at the bottom axis on the graph, it demonstrates that as the steam gets wetter, it's got less energy contained within it. So it's a double whammy. Everything we do with regards to good practice in steam systems should be with the intention of keeping the steam as dry as we possibly can. So there are other fundamentals we need to give thought to whenever we're looking at steam generation. A kilogram of water going into the boiler. It's a non-compressible fluid, so it's going to have a volume of 1 litre or 0.001 cubic meters. And as it changes state to produce steam as a gas, it's expanded so that that same kilogram has now got a volume of 1.673 cubic meters. It's expanded to a factor of about 1,673 times. But in reality, our client's going to be generating steam under pressure, 10 bar gauge. And we remember the benefit of generating steam at that pressure where we can reduce its volume. Now, we've also mentioned that we need to have a pressure drop around the steam system. We've got to have a fall in pressure. So as that steam falls in pressure, whether it's across a pressure reducing valve, a control valve, or even across a steam trap that might have failed in the open position, what we're going to see is the fall in pressure brings around an expansion of that volume. So using the example of a steam trap that may have failed in the open position or an incorrectly sized pipework, we're at risk that we could have a significant expansion in that volume of steam. That's why we see flash steam vents located periodically around a steam and condensate loop. It's in order to protect the infrastructure from significant expansion that could do damage. So that explains the pressure volume relationship. We've also got the pressure temperature relationship, and this is critically important to understand. So we've mentioned that at 0 bar gauge, water boils at 100 degrees, and therefore the temperature of the steam at 0 bar gauge is also 100 degrees. In reality, our client is going to be producing steam under pressure, and at pressure of 10 bar gauge, well, that water is going to boil at 184 degrees. Therefore, the temperature of the steam is 184 degrees. If we've reduced the pressure, in order to manipulate the pressure at the process, let's say the pressure has fallen to 2 bar gauge to control the temperature at 130. Well, it tells us that we can do that by observing that pressure temperature relationship using a very, very simple and basic pressure reducing valve in order to do that. It also tells us the importance of having a sufficient number of pressure gauges around the network so we can accurately commission and determine what's happening within the steam system. So this demonstrates the relationship between the pressure and temperature of the steam, but it also shows us the relationship between the pressure and the temperature of the condensate itself. And that's important to understand because when the steam gives up its heat energy, that's the useful heat energy that are demonstrated in that box in blue on the previous slide. When the steam gives up that useful heat energy, it condenses, changes state from a gas to a liquid, and the liquid condensate that retains the sensible heat. It retains the heat that is unable to be imparted to the process. So steam actually gives up its energy isothermically. There isn't an exchange of temperature. So that heat loss, the condensate that exists in the distribution pipework, that's actually going to exist at the same pressure and the same temperature as the steam does, and the same at the process. So if we had a steam trap that failed open, the steam pressure could be 10 bar gauge and then falling in pressure very, very quickly to somewhere close to atmospheric. So of course, we're going to see that sudden expansion of the steam. But we're always going to have condensate upstream of the steam trap as well. So if the condensate exists as a single phase liquid, 10 bar gauge, 184 degrees, as that condensate falls in pressure, it can no longer exist at the same temperature. It can only exist at a temperature of 100 degrees at atmospheric. So it's got to cool down very, very quickly in a short space of time. And the only way that condensate can cool down is by a certain percentage or a certain mass of the condensate boiling off. In other words, it changes state from a liquid back to steam again. And we call that flash steam. And we remember that because condensate is a non-condensable liquid, as it changes state from that liquid back to steam again, that expansion is going to be to a factor of 1,673 times. We remember that those flash steam vents are sited periodically to protect the infrastructure, but they are representative of an inherent inefficiency. And we want to be aware of them and we want to identify them wherever we can. So I'll come back and I'll talk about the principle of flash steam as we go through some of the further solutions. But moving forwards, we've identified that it's the generation of the steam today that has a heavy burden in terms of fossil fuels, and therefore is representative of carbon emissions and an inefficiency. So it's the point of generation in the steam boiler house, the energy centre, that we want to be focusing on first of all. And the energy centre is typically located at the far reaches of sites for logistical purposes, and then we distribute that steam hundreds, thousands of metres around site. So as we've mentioned, it's highly likely that we're using natural gas at the moment to generate steam, but in the very near future, it's highly likely that we'll be able to use hydrogen. Well, We're all aware of the benefits of burning hydrogen. If we combust hydrogen and oxygen together, the byproduct is water, and therefore we simply don't have any carbon emissions to worry about at the point of combustion. Of course, that really depends upon how the hydrogen is manufactured in the first instance. So there is some debate ongoing with regards to the advantages of grey, brown, even blue hydrogen. And it's far, far better if at some point in the future we may have the possibility to electrolyze water local to site, maybe using renewable energy to electrolyze that water from aerothermal or solar sources. Because if that is the case, then we're able to guarantee that we've completely um, move towards a decarbonised production of steam. We've got no reliance on fossil fuels to supplement the manufacture of that hydrogen. Now, Spirax Sarco, we're not combustion experts, we don't pretend to be, but we have been working with a number of steam boiler and burner manufacturers here in the UK to identify that if and when our client is in a position to produce green hydrogen on site, then it may simply be a case of removing the existing natural gas burner from the steam boiler and replacing it, retrofitting it with a new hydrogen burner. By doing so, we've retained the existing water treatment regime on site. We've retained the existing steam boiler. We've retained the existing steam distribution network and all of the heat exchangers. We can decarbonise steam production whilst retaining the existing infrastructure. Now, hydrogen burners are at a very, very advanced stage of commercialisation and likely to be available to the market in the very, very near future. But in the meantime, our colleagues over at Chromalox and the other members of our electric thermal engineering division, they've been generating steam from electricity for a number of years. It's just that it hasn't always been commercially viable when we scale it up to larger industrial processes. But those standalone electric steam generators, they do bring around a significant number of benefits, as we can see on the screen, because it's easy to fully automate them, because there are no naked flames, there are fewer health and safety concerns. We can operate them with a greater degree of reliability, the lower maintenance, easy to automate. And of course, we know that at the point of combustion, if we're raising steam from electricity, there are no harmful carbon emissions. So that can be a significant key benefit for a client who may have identified that the cost of electricity is a little bit more than the cost of gas, but at least they don't have those carbon emissions to contend with. And it can help them achieve their sustainability targets. But again, we've got to remember that whenever we're generating steam from electricity, there's only so much energy we can get down an electrical cable. So we really need to be satisfied that the infrastructure that's bringing the electricity into the boiler house is capable of providing the electricity that is required instantaneously whenever there's a demand. And that's something that's challenging to do when we compare that to a traditional natural gas steam boiler. Now, when we've got a process where it is viable for us to do that, or we are able to upgrade the electrical infrastructure, we could have a standalone electric steam generator, or we could retrofit, we could remove the natural gas burner, and we could replace it with an electrification kit. In other words, we can use the existing steam boiler, remove the burner, and put an electrical element on it. Again, we're retaining the existing water treatment regime, the existing steam boiler, and the existing infrastructure. It means that we can produce steam in exactly the same way that we were doing before, but we've moved towards that net zero. Now, taking that one step further, Spirax Sarco has also got a product that's at a very, very advanced stage of commercialization. It's what we call the steam battery. And the steam battery, it's a kind of thermal store. And thermal store are very common in other industrial applications. But the way the steam battery works is, well, if we take a pressurized vessel of water, if we elevate the pressure and elevate the temperature, we can go back to the fundamentals on the steam tables that we looked at. Let's say we elevate the pressure of the thermal store to, let's say we elevate it to 30 bar gauge. That means the water's sat there as a single phase liquid at 225 degrees. So whenever we've got a requirement for thermal energy in the form of steam at the process, that can be realized by nothing more than depressurizing that vessel. That's when we get that flash steam effect that we spoke of. The water's going to boil off, change state to steam. In other words, we can distribute that steam to the process, to the heat exchanger, in exactly the same way that we were doing previously with the steam from the natural gas burner. Now, we can charge that thermal store using electrical energy. And that electrical energy, it could come from the grid, and we could take a number of hours, perhaps during the silent hours of the night when the electricity is at an attractive tariff in order to do that. But we can also use renewable energy. We can use solar, we can use aerothermal. So while ever that renewable energy is available, we can use 100% of it to charge that thermal store. So the way the thermal store is likely to have significant benefits moving forwards is how it compares with alternative sources of energy. Let's say, for example, an electrical battery. Electrical battery, we use them all day, every day, charging our mobile phones. We appreciate what the benefits are. The supply and demand can be decoupled. But one of the downsides really is the fact that that's only useful for electrical energy. It's got no value, or it's impractical to use it for thermal energy purposes. Many of us are aware of the benefits of traditional steam accumulators, especially if we're working in heavy industries. We know that steam accumulators can only store thermal energy, they can't store electrical energy. So it means that we've got that reliance on fossil fuels, as we have with the traditional steam boiler. An electrical steam generator or an electrical boiler, well, it means that because we can only generate that steam, that thermal energy instantaneously, we can't store it. It means that the infrastructure upstream of the burner, upstream of the boiler, may need to be significantly larger than it is at the minute, because we've got to be capable of ensuring that the supply can satisfy the demand. So that may be a challenge. So the steam battery, that thermal store, it's got a significant benefit because it brings all of those advantages together into one common solution. We can use electrical energy in the form of renewables to generate and then store that thermal energy until such a point that it's required by the process. So we can spend a significant period of time charging the thermal store, only to release that energy at certain parts of the day whenever there may be a particular process requirement. So a typical thermal store, you can see a picture of myself there stood next to a thermal store that we've got in operation at the moment. This particular thermal store, it's got a capacity of 14 cubic meters. Typically, we would fill it to around 80% full, so around 12 cubic meters of water. So that means we've got a steam space at the top of the store. So it means that if we charge that thermal store to 30 bar gauge, for example, if we were then going to drop the pressure downstream of the thermal store to somewhere around 1 bar gauge, it means we'd have approximately 1800 kilograms per hour of steam available, which equates to an energy of approximately 1 megawatt per hour for the process. So by moving towards a thermal store, this is a significant advantage for a significant number of steam using sites in helping them to move towards decarbonisation. So I've just got a quick animation I'd like to play at this point, just to give you a quick refresher on some of the working principles and advantages of the work of the thermal store, the steam battery. So we can use electrical energy in multiple forms. It can come from aerothermal, solar. It can even come from the grid during the times when the wind's not blowing or the sun's not shining. But whilst that whilst that renewable energy is available, it will use 100% of it and store it thermally in the form of charged hot water until such a time that the process requires that thermal energy. Steam at the end of the day. The process doesn't care how that steam's going to be generated. It's basic physics. We're depressurizing hot water to produce that thermal energy. So it's highly likely that in the coming years or months, it's highly likely that a steam using site will have a number of different steam generation solutions. They could use hydrogen. They could use electrical energy straight from the grid, and they can also use a steam battery to supplement it. And if they're doing that, then it's possible that they can move towards a total decarbonisation, but retain the existing steam infrastructure. That's fundamentally important. Very little cost or disruption to the process outside of the boiler house. And talking about the process, we also want to look at what we refer to as demand reduction. Demand reduction means that if we can use the steam or the thermal energy outside of the boiler house, outside of the energy centre more efficiently, then we're reducing the demand for steam. If we're reducing the demand for steam, we're reducing the amount of fuel that's required, and therefore we're reducing those carbon emissions. So one such process that's a little bit quirky, it is quite niche, but it does have its place in heavy industry, doesn't necessarily have to be coupled to a steam system. We can use other sources of thermal energy, such as hot effluent in the form of wastewater. Well, many of us are already familiar with a traditional organic ranking system, and that can traditionally only take the waste heat energy out of an effluent stream at temperatures in excess of 120 degrees. Well, we've got a product that we call the CPC, or the controlled phased cycle. And that's able to take the energy out of waste effluent at much, much lower temperatures, typically as low as 70 degrees. But obviously, the higher the temperature, the more waste heat energy is going to be available for reuse. And a CPC is a typical skid mounted unit. And essentially, it takes the waste heat energy from the effluent stream, it passes it across a thermal barrier, it causes the gas on the secondary side to expand. That expansion spins a turbine, and that turbine generates a small amount of electrical energy. The key word here really is a small amount of electrical energy. Because the CPC essentially cools that waste heat stream, one of the key cost saving benefits is if our client was paying for an additional source of energy to cool that effluent. So the CPC could sit in place of a cooling tower, for example, or it could be used for perhaps cooling the jacket of a CHP system, for example. By cooling that waste effluent and generating a small amount of electrical energy, well, that electrical energy combined with the cooling that's no longer required is going to demonstrate a payback. So I've got another little animation that I'd like to play here. And this really just demonstrates some of the key benefits of the CPC. So heavier industries, it could be cement manufacturing, steel works, tyre presses. They may have a significant amount of waste effluent that is going to waste, and they may be paying a significant charge for that effluent to be cooled across a cooling tower. Well, by removing the cooling tower, moving towards a CPC, not only have they reduced the burden of maintenance, the operational costs, the water treatment costs of the cooling tower, it now means that we can generate a small amount of electrical energy that could be then taken to the local area network. Now, if there is a waste heat or a waste effluent stream that could benefit from such a project, then we can very easily identify if the mass flow rates and the temperature profiles is sufficient to demonstrate what we expect to be. So the CPC, exactly the same way that the steam battery is, it's a product at a very advanced stage of commercialization. We've got a number of these solutions out in a number of different test functions around the UK. So we also know that we want to monitor the accuracy and we want to monitor the overall efficiency of the steam distribution network. So some form of connectivity is likely to be of key importance. Now, the vast majority of steam using sites will have a traditional steam trap survey of sorts. That's when the engineer will wander around site. He'll either scribble down notes or he'll be speaking into a dictaphone, identifying when a steam trap may be in the failed open or the failed closed position. It may take some weeks for that report to be compiled and then issued to the correct person on site. So there can be a significant delay between identifying an inherent failure and the client being in a position to rectify it. Well, we've now got some very unique software in the form of a handheld survey tool, and that's capable of identifying a trap's condition, failed open, failed closed, and sending information via the cloud to some software. And that can pull together a report and send that information to the client in real time to help them identify the overall financial efficiency of their wider steam trap population. They can configure their own alarms so they can identify the key points of inefficiency on their steam system in real time. And they can quantify that both in terms of the energy that's being lost and the financial impact that that lost energy can have. Obviously, if we're minimizing the amount of steam that is being expelled to atmosphere, we're reducing the demand for steam, and by nature, we're moving towards a decarbonised steam system. And taking the subject of connectivity one step further, we're now able to connect a gateway to a vast number of the solutions that we may have, the different items of capital equipment, not just in the boiler house, but around the wider steam and condensate loop. And the benefit here is traditionally, it may well be some weeks or months until such a time that a maintenance engineer has identified that he thought he had an inefficiency. It may then be a week until a steam expert is able to visit site to verify that. And that steam expert may then have to call upon a service engineer who may need to wait for a number of spare parts before that problem can be identified. There may need to be several visits to and from site, which isn't doing the carbon footprint or the image of the entity in question any favors. So if we're able to identify a failure or an inefficiency of a component in real time, then we're able to help our client to diagnose that problem. They may have the skill set on site to be able to rectify the problem, just not necessarily to diagnose it or quantify it financially. So these gateways can be fit to any number of different steam equipment, ranging from the hot well, the boiler, even the steam battery that we've spoken about. And then at the process, the heat exchangers, the condensate recovery systems, if we're able to monitor and identify whenever a piece of capital equipment is starting to operate inefficiently, we can identify that, we can report that back to the client, and we can demonstrate a significant payback. We can reduce the demand for steam and ensure that they're moving towards net zero or decarbonisation of their steam system. Well, so far I've spoken about a lot of the products that have either just been commercialized or at a very advanced stage of commercialization. But it's critically important that we remember that key phrase demand reduction. We could invest in all of the modern products and solutions I've spoken about, but if we're not observing good working practice in the operation and maintenance of our steam system, the effect is the same as investing in a very modern and efficient combi boiler at home and then going out and leaving the hot tap running all day. It's pointless. We need to remember the good working practice. And these are the things that we can do here and now to put our steam system in an excellent position for moving towards the next level in the coming months or years. So the good working practice, the basics we want to remember, it's things like making sure that our steam traps are adequately monitored so that they're not left failed in the open position. We want to keep the water in the hot well, in the feed tank, at the highest point possible. Remember, the steam tables tell us the hotter the water we're putting into the boiler, the less energy we need to consume to raise steam again. And one such way that we can keep the hot well at the nice high temperature is by recovering as much of that condensate as we possibly can. We want to keep the steam as dry as we can. Remember, dry steam's got more energy in it. So we want to design the infrastructure such that the condensate can drain away across the appropriate number of the steam traps in order to remain as dry as possible. We want to install the appropriate number of separators around site, again, to scrub out any moisture that may be present in the steam and help us to keep the steam as dry and energy dense as we can. Reducing heat losses in the infrastructure with adequate insulation. Reducing the heat losses, we're reducing steam demand. Therefore, we're operating with a greater degree of efficiency. The boiler blowdown controls, we want to make sure that they're automated wherever possible. If we've got manually operated blowdown controls, it's nigh on impossible to understand the amount of hot water we're putting to waste. And then we also want to keep an eye on those flash steam vents. Well, remember, there's just as much energy in that flash steam as there is in plant steam. So we really want to think about, whenever we see a flash steam vent, we want to think about, well, is there anywhere else that we could actually use that heat energy? Could we make use of it at any other process? If we can, it's free energy. We just need to divert it somewhere else. Now, maybe we can use a very complex flash recovery energy management skid for certain high yield processes. We can demonstrate a very attractive payback. But even if we can't, even if we've got nowhere where we can use the energy that's contained within that flash steam, if we can at least just condense it or condense as much of it as we possibly can, we're still providing that expansion brake. It just means that by condensing as much of the flash steam as we possibly can, we're increasing the mass of condensate that we can get back to the boiler house. And if we're increasing the mass of hot water that can be diverted back to the boiler house, then of course we're reducing the amount of energy that we need to raise steam again. So different solutions that we can use to make use of that flash steam, they can vary from the very basic flash vessels through to the more sophisticated and complex flash recovery energy management devices. It really comes from understanding the mass flow rate of condensate and the pressure drop that it undertakes. Once we understand that, the calculation's an easy one, and it's very easy to demonstrate what the payback is likely to be in financial terms. And one last solution that I'd like to discuss is by no means a new or futuristic solution, but it's one that perhaps isn't adopted as often as it should be here in the UK. It's what we call a pressurized deaerator. Now, many steam using sites are familiar with holding the water atmospherically in a hot well or a feed tank, but by elevating the pressure or the temperature to somewhere around 0.2 bar gauge, it means we can elevate the temperature of the water to 105 degrees. So we've got even hotter water going into the boiler. Therefore, we need to consume even less fuel to raise steam again. Other benefits include an improvement in water chemistry, which means we don't have to blow down as much hot water from the boiler. So we've reduced the thermal losses there. But because the pressurized deaerator is pressurized to 0.2 bar gauge, this is an excellent place for us to recover all of that flash steam that was previously being vented away and lost. So it means we can now move very, very close towards a zero net loss steam distribution system. So I have very quickly put a few points of summary together for you on the slide deck. The PDF of the presentation will be made available for you, for those of you that may like to refer to it in any point in the future. And of course, the video will be uploaded onto the IMechE YouTube channel in due course. This is one of a series of CPD presentations that we offer. So if there is any interest in these series of presentations in the future, either for your individual companies or for IMechE as a whole, would be very, very pleased of the opportunity to make those available. So I'd like to thank you once again for attending today's presentation. Thank you, Murat, for the invitation. Thank you for hosting. If there have been any comments or any questions placed into the chat box, then Murat, could I please ask that you open up your microphone and take the opportunity to shout those out to me?
Thank you very much, Dan. It's been an interesting presentation. I think the steam battery especially raised some interest, actually. We received some questions around that, what would be the maximum capacity for a steam battery? And perhaps what would be the service life of it? How long would they really last in operation?
In terms of, I'll answer the last question first, if I may. The service life, it's the same as think of it as a boiler without the burner fitted, really. So it's a question of ensuring that we've got an adequate maintenance and water treatment regime. The water treatment needs to be exactly the same as it does for a traditional steam boiler. So we are working very closely with the appropriate authorities, the likes of the CEA and BOAS, in order to recognise this as a component that should perhaps have its own guidance documentation written. But in very basic and layman's terms, the actual component is simply a boiler without the burner installed. So good basic water treatment and adequate blowdown and control of the water that's held in storage should provide a comparable life to the traditional fired steam boiler.
Maybe to give some idea to people who have no experience of these things, would you put down some numbers like 10 years, 20 years, perhaps?
Would I? Well, I'm putting my head in the noose there a little bit,
Okay.
Murat, because we're Spirax Sarco are not boiler manufacturers, but I may have a few colleagues that have dialed into the CPD presentation tonight that might want to contribute to that. But I would imagine that it's feasible to expect a life cycle of 20 years. When it is operated in accordance with the correct water treatment and blowdown regime.
Okay. That's perfectly fine, I guess.
There was a question on the capacity as well. The capacity is in terms of physics and fundamentals, we're not restricted on capacity. However, manufacturing processes dictate that once we get beyond certain sizes and certain capacities, then the gauge thickness of the plate and rolling the plate and manufacturing techniques get more complex. So typically we would expect that we'd be moving towards the larger size. If we were looking at a capacity of 14 cubic meters, which was shown in the photograph with me stood alongside it. But of course, there's nothing stopping us banking the thermal batteries as we would do, with our batteries in our TV remote control at home. We simply have multiple batteries, and the benefit there is we've got that thermal energy in storage for different processes at different times of the day.
So the limitation really is the space, I guess, and the size of steel you can actually.
Absolutely, and
probably.
we need to be clear. We need to be clear that, you know, if you're holding, you know, 14 cubic meters of water in storage, then it's not going to be a smaller boiler house than the existing steam boiler is located in. You know, we need to be clear about managing expectations there.
Excellent. Okay. Another question is around, are there like any trial sites in the UK for the steam batteries? Have you got any
Yes, we do. We
in
do.
operation?
At the moment we've got if I remember rightly, we've got 3 sites where these are operational and have been operational for some time. They've been operational certainly in excess of 4 or 5 months. They do have that gateway fitted that we spoke about. So we're monitoring the information so we can trend the data and make sure that the performance is exactly as it should be. We've got one that's fit in an NHS application, and we've got one that's fit in a building service application, and I believe we've got one that's about to be installed in, I believe it's a food and beverage manufacturing application, but I'm prepared to be contradicted by any of my colleagues that may be dialing into today's presentation.
Okay, I'll watch out for their comments then in the chat. Another sort of statement, sort of question. Could you say like the steam battery is sort of very similar to an unfired steam generator, like pretty much exactly the same thing?
Kind of, yeah, it's very similar. I think it's got similarities with a number of different steam generation solutions. As we mentioned, it's got the ability to decouple supply and demand, so we can charge the battery or charge the store at our leisure and release the energy as and when it's required. So we've got that flexibility that an electric steam generator doesn't have. We don't need the steam. We don't need the constant supply and demand being matched as we do with an electric generator. It does work very, very similar to a traditional steam accumulator, but it just means that we just simply don't have that reliance on fossil fuels that we would have done previously.
Okay. Okay. Another question here. Let me just read it again. So the question, if I can interpret it correctly, the thermal battery, if maintained correctly and the water treatment is correct, then it should last for a couple of decades or more as a normal steam boiler would. So this is sort of a answer to our question, I guess.
Yes, yeah, absolutely. I think in very basic and layman's terms, any steam boiler operator will be very comfortable with this solution. It doesn't have the burner on it. We've taken the burner off the boiler, and we're essentially using electrical energy in order to charge that vessel. So we'll have the same blowdown controls, the level controls, we'll have the same TDS control, we'll have the same water treatment requirement, and the steam that's being produced from the top of the solution into the header is going to be exactly the same as the steam that is being produced by a traditional burner. So as long as the water treatment regime is kept exactly the same as we'd want to keep with a traditional fired boiler, then we're going to expect the same longevity that we would do with the traditional fired boiler.
Yeah, yeah. Another question came in about probably what is the sort of standard range or the standard size or capacity that you offer, maybe if you get the maybe smaller size or the standard size you have, what would be the capacity for those systems?
Well, again, we'd have to look at the requirement on its merits.
Okay.
So we'd look at I mean, these are typically bespoke design solutions. So we'd have to look at how much steam the process required, whether it was a centralized or decentralized process. But as we've mentioned, the limiting factor it is largely going to be the footprint of space that the client has available. But once we get much beyond 14 cubic meters of water that's going to be held in storage, then of course the manufacturing processes and manufacturing techniques may place a financial constraint on the project. But it may be viable for the client to have a thermal battery or a steam battery in one part of the site, supplying steam to a certain number of processors, and the same in a different area of site. The client may be able to overcome that challenge by moving towards some form of decentralization.
I understand. One question from me, I guess, is steam to me seems like a vessel to transport the energy from one place to another. And this obviously storage and battery concept is quite attractive. Do you see in the future the steam will sort of take over any industries, or it will take away from the electricity, like the electricity storage units, like normal electric batteries in any way? Do you foresee anything like that?
The possibilities with steam are endless, and one common, I call it a criticism, but one common negative comment that we often have is that, well, steam's been around for years, it never changes, and people generally associate it with the Industrial Revolution. You know, you conjure up images of the Flying Scotsman. And it comes, you hit the nail on the head, Murat, when you said that steam is the most efficient carrier of heat energy. Now, people associate the fossil fuels that have traditionally been used to generate the steam with the steam. Well, if we can use renewable energy, clean energy to generate steam, then of course we've got green steam, we've got sustainable steam. The image that I showed up very early on to the presentation, it demonstrates that we can get so much more energy down a steam pipe than we can down an electrical infrastructure, for example. Can you imagine a nuclear power station without steam? We'd be unable to move the turbines without steam. So as more and more nuclear power stations are being built, steam is only going to increase in relevance. That's before we look at other sectors such as the food, beverage, pharmaceutical sector. Steam will always be relevant, and there'll always be a requirement for steam. We've just got to be a little bit more open to the possibilities of generating steam from sources of energy that are green, sustainable. And now we can do that.
Thank you so much, Dan. It's been a very interesting presentation, very interesting content. We are a bit over time, but I think people appreciated it. We have quite a few attendees here. Like I mentioned, I will make sure everybody who is registered will receive the PDF version of the slides, and I will make sure this is also uploaded to IMechE's YouTube channel. And thank you all very much for all your questions and contributing to this presentation, and we look forward to seeing you in our future events. So please go back to your IMechE near you website and check our new further events. And feel free to contact me as well to ask for a CPD certificate. Thank you again, Dan. Thanks very much.
Thank you, and good night, everybody. Thank you for attending.
Cheers.